In previous section, we have solved several problems involving uniformly accelerated motion along x-axis. In this section we will be discussing free fall, that also employs motion with constant acceleration, but this time along the y-axis or vertical line. When we say free fall, it is a type of motion with constant acceleration due to the influence of the Earth's gravitational attraction. This gravitational attraction, or gravity, is exerted on all bodies and is nearly pointing to the Earth's center. Some examples of free fall are throwing a ball straight up in the air, a diver jump from a diving board, and a ball drops freely from your hand. In the 4th century BC, Aristotle, a Greek philosopher, thought that a given body falls faster than lighter ones. This was accepted as fact until the Italian physicist and astronomer Galileo Galilei conducted his experiment, in 16th century, with two objects of the same material but different weights dropped from the Leaning Tower of Pisa. His experiment concluded that all bodies initially having the same height would fall to the Earth's surface at the same time. Although the result of Galileo's experiment on falling bodies is accepted, influences besides gravitation are unavoidable. Air resistance in the Earth's atmosphere, distance of the falling object from the Earth, and the Earth's rotation are the three major things that affects falling body. Therefore, he pointed three assumptions to make his experiment valid. Number 1, air resistance is neglected. Consider a glass tube filled with air. And there are two objects, a heavy metal and a light feather. With the presence of greater air drag on the feather as compared to the metal, we see that the metal falls faster than the feather. But once air is evacuated from the glass tube, they would fall at the same time since the effect of air drag is eliminated. Number 2, the effect of Earth's rotation can be neglected. Imagine this is the Earth's center, which has a distance radius from the surface. At a location near the equation, the Earth's surface is moving at a linear speed of around 460 meters per second. If we released a ball at a certain height h, its point of impact will be affected somehow by the Earth's rotation. Here, we will neglect that effect. Lastly, number 3. The height of fall is very less than the Earth's radius since the gravitational attraction decreases with elevation. We will take a look in more details on the effects of variation of gravity later. Now let us consider the kinematics of a free fall. First thing to discuss is the acceleration due to gravity, which is denoted by small letter g. In small region, near the Earth's surface, the acceleration due to gravity is uniform in both direction and magnitude and is equal to 9.8 meters per second squared in SI unit system, and 32.2 feet per second squared for English system. As you can see in the figure, we neglect the variation of the magnitude of gravitational acceleration for a small region near the Earth's surface. And this is what we are going to apply. We will follow the third assumption of Galileo. However, if we take a look on larger and farther regions, the magnitude decreases with increasing elevation. So at farther regions the gravitational acceleration is less than 9.8 meters per second squared. A free fall may be in two scenarios, falling and rising. The magnitude of the velocity of a falling body is increasing by 9.8 meters per second for every second. It means that when you release an object from rest, the magnitude of its velocity becomes 9.8 meter per second 1 second later. It becomes 19.6 meters per second 2 seconds later, 29.4 meters per second 3 seconds later, and so on. In terms of the magnitude of vertical displacement, we see that it is increasing in each second. With these changes in velocities and displacements, we assume that the gravitational remains constant. Now let us investigate how the motional graphs look like for a falling body. For the position time graph, since a falling body moves downward and if we take the origin at higher location, the positions as function time are negative values. For the velocity time graph, The velocities are negative values since a falling body moves along negative y-axis. We see that the magnitude of velocity is increasing as it falls. In other words, a falling body accelerates. On the other hand, a rising body is decelerating at the constant rate of 9.8 meters per second for every second. When we throw an object vertically upward with an initial velocity of 29.4 meters per second, because of the opposite direction of gravitational acceleration, its velocity becomes 19.6 meters per second 1 second later. 2 seconds later its speed becomes 9.8 meters per second. And 3 seconds later, the object momentarily stopped, hence the velocity is zero when it reaches the maximum height of flight. Also we see that the magnitude of its vertical displacement is decreasing in each second. Again, although both the positions and velocities are changing, we assume that the acceleration due to gravity remains constant. We can also say that a rising body is decelerating as it rises. For position time graph, since a rising body moves upward and if we take the origin lower location, the positions as, of course as function of time, are positive values. For the velocity time graph, the velocities are positive values since during its course all the way up, it moves toward the positive y-axis. We see in this graph that the magnitude of velocity of a body is decreasing as it rises. Now you're going to learn the related equations for free fall. We consider first a falling body. At an initial time 0, the body is at initial position y sub I from assigned origin with an initial velocity of v sub I. We knew already that a falling body accelerates due to gravity, so at later time t, both its position, the final position y sub f and the velocity v sub f have changed. On the other hand, for a rising body, the body is at initial position y sub I from the origin at time 0. At this point it has an initial velocity of v sub I. As it moves against the gravity and the position has changed to y sub f, the magnitude of its velocity is decreased to v sub f. Now, it's time for the equations. Since we already assumed that a free fall has constant acceleration in small region near the Earth's surface, we can use these 5 equations for uniformly accelerated motion. You should not forget these equations. These equations are very useful in many aspects of physics, especially when we are dealing with Newton's second law of motion in next unit. So how we are going to use these equations for motion of free fall? It is very simple. Since a free fall follows a vertical path as it moves, we only change the position x to y. And the acceleration a will be changed to negative of g. We put negative sign besides g because g is always downward. Doing these things, so equation 1 will become final velocity v sub f is equal to the initial velocity v sub I minus gravitational acceleration g multiplied by time t. Second equation will be final position y sub f minus y sub I, so this is also the displacement delta y, is equal to the half of the sum of the initial and final velocities multiplied by time t. For third equation, y sub f equals y sub I plus v sub I t minus 1/2 gt squared. Fourth equation is y sub f equals y sub I plus v sub f t plus 1/2 gt squared. And for the fifth equation, v sub f squared equals v sub I squared minus 2g multiplied by the quantity y sub f minus y sub I. These are the 5 kinematic equations for free fall. Take note that these equations are applicable for both scenarios, falling and rising. You do not need to make some adjustment on the signs of variables, especially the sign of gravitational acceleration in the equation. The equations always fit for both falling body and rising body. Be careful also on the signs of the velocities. As the body moves upward, its velocity is positive. But once the body moves downward, its velocity becomes negative. Do not forget and always follow this very important sign convention for velocity. Aside from understanding these free fall equations, keep in mind the following important points. The initial velocity v sub I is 0 if the body is initially at rest and drops freely. The final velocity v sub f is 0 if the body has reached the maximum height of flight during rising. When a body is thrown vertically upward, it will reach the maximum height at a time, let's say 2 seconds, equal to the time it took from the maximum height to its original position, so the time of fall is also 2 seconds. With this, we can say that the time of flight is equal to the sum of time to rise and time to fall. Do you have any questions in mind? You can clear things out by communicating with your teacher or have online collaboration with your classmates. Okay, now let's answer this free fall problem. Problem number 11. You throw a ball vertically upward from the roof of a tall building. The ball leaves your hand at a point even with the roof frailing with an upward speed of 15 meters per second, the ball is in free fall. On its way back down, it just misses the railing. At the location of the building, g equals 9.8 meters per second squared. Find, letter A, the position and velocity of the ball 1 second and 4 seconds after leaving your hand. Letter B, the velocity when the ball is 5 meters above the railing. Letter C, the maximum height reached and the time at which it is reached. We first established given information. The initial velocity is positive 15 meters per second. This is positive because, according to problem statement, the ball is thrown upward. It will be negative if the ball is thrown downward. Be careful on this, or else our solution will be messed up. G is 9.8 meters per second squared. We set initial position y sub I to 0, since we choose the thrower's hand as the origin. And we have two indicated time 2 seconds and 4 seconds. Required quantities are the final position and final velocity at 1 second and 4 seconds. Final velocity when the position of the ball is 5 meters above the railing. Maximum height and the time it reaches this position. To begin our solution, we put the ball on y-axis to visualize its position as it moves. So we have given the initial velocity positive 15 meters per second. We have set the initial position to 0 at time 0. Letter A, for the final position and final velocity at time 1 second and 4 seconds after throwing the ball. We use equations 1 and 3 for v sub f and y sub f, respectively. V sub f equals v sub I minus gt. And y sub f equals y sub I plus v sub I t minus 1/2 gt squared. So at 1 second, applying equation 3 then substituting the given information, 15 times 1 minus 1/2 of 9.8 times 1 squared. The final position is positive 10.1 meters. Positive value means that the ball is located above the railing 1 second after throwing the ball. For final velocity, from equation 1, then substituting the values 15 minus 9.8 times 1, will give a final velocity of positive 5.2 meters per second. Positive velocity indicates that at time 1 second, the ball is still moving upward. At 4 second, we will do the same procedure while changing the time to 4 seconds. So the position of the ball 4 seconds later is negative 18.4 meters. Negative value means that the ball is located below the railing 4 seconds after throwing the ball. For final velocity, using again equation 1, its value is negative 24.2 meters per second. We see a negative velocity since it indicates that at time 4 seconds the ball is already falling. Let's continue to letter B. We calculate the final velocity of the ball when the ball reaches 5 meters above the railing or thrower's hand. Since we do not have available information on the time when the ball reaches this 5 meters, the appropriate equation to be used is equation 5, that is v sub f squared equals v sub I squared minus 2g times the quantity y sub f minus y sub I. Remember, this is the only free fall equation that do not require time. Then, we take the square root both sides of the equation. Substituting and pressing on the calculator the values, will give a final velocity of positive and negative 11.3 meters per second. So what this positive and negative signs mean? Try to observe that the ball reaches a position of 5 meters above the railing of the building twice. First is that when the ball is still rising, so the velocity here is a positive. Second is when the ball started to fall from maximum height and eventually it will reach again this 5-meter position with a negative velocity. For these reasons, we take two answers positive and negative 11.3 meters per second. Lastly, letter C, for maximum height and the time at this point. Maximum height is a special term for final position y sub f when the final velocity is 0. We do not know yet the time, so we use again equation 5 for this. But we need to transform the equation because we want to know y sub f. So we will do some algebraic manipulation. Here we transposed v sub I squared to the other side of the equation. Then we can cancel out y sub I, since it is 0. Then dividing both sides by negative of 2g. So the transformed equation y sub f is equal to v sub f squared minus v sub I squared all over negative of 2g. Substituting values will give a maximum height y sub f of 11.5 meters. Take note this is the maximum position of the ball. It will never reach any position above this. Then for the time, we simply use equation 1. Again we manipulate the equation to solve for time. We transposed v sub I to the other side and dividing both sides by negative g. So time t is equal to the change in velocity v sub f minus v sub I divided by negative of g. Substitute the values, will give a value of 1.53 seconds. It means that right after 1.53 seconds, the ball begins to move downward. We see, in previous problem, we set the initial position of the ball to 0 since we choose the thrower's hand as the ball's arbitrary origin. That is not always the case. In this problem, we shall see that we can assign any point in space as reference origin. Problem number 12. A hot air balloonist, rising vertically with a constant velocity of magnitude 5 meters per second, releases a sandbag at an instant when the balloon is 40 meters above the ground. After it is released, the sandbag is in free fall. Letter A. Compute the position and velocity of the sandbag at 0.5 seconds and 2 seconds after its release. Letter B. How many seconds after its release will the bag strike the ground? Letter C. With what magnitude of velocity does it strike? Letter D. What is the greatest height above the ground that the sandbag reaches? Now let us establish the given information. Although the balloonist only releases the sandbag, we do not set the initial velocity of the sandbag to 0. Instead, the sandbag's initial velocity is positive 5 meters per second, since the hot air balloon is also rising at this speed. Now instead of assigning initial position to 0, we set it as 40 meters above the ground. Here, we will use the fixed ground as our origin so the initial position of the sandbag is positive 40 meters. Then, we have also two indicated times 0.5 seconds and 2 seconds. So for letter A, we need to solve the final positions and final velocities at time 0.5 seconds and 2 seconds. Letter B, the time for the sandbag to reach the ground wherein the final position is 0. Letter C, the final velocity as the sandbag hits the ground. Letter D, the maximum height reached by the sandbag, that is when the velocity is 0. Before we proceed, I want to reiterate that we do not set the initial position to 0 because we choose the ground as the origin, which I guess more appropriate since the ground is fixed. We do not set the hot air balloon as the point of origin because it is moving upward. Therefore, it is more appropriate to set the initial position as 40 meters. Now we use equations 1 and 3 for the final position and final velocity, respectively. At 0.5 second, using this equation and substituting the given information, the position of the sandbag is 41.275 meters above the ground. For the velocity at 0.5 second, equation 1 will give a velocity of positive 0.1 meter per second. At this point, the sandbag is still rising since the velocity is positive, although its magnitude is close to 0. At 2 seconds, we use the same formulas. So the final position is 30.4 meters, which is less than 40 meters, which means that the sandbag is already moving downward 2 seconds later. So later we will see that the velocity should be a negative value at this time. For the final velocity, v sub I minus gt, substituting the values, will give a final velocity of negative 14.6 meters per second. As expected, this negative sign indicates that at time 2 seconds the sandbag is already falling. For letter B, we are going to find the time for the sandbag to reach the ground. Now since we selected the ground as origin, therefore we set the final position y sub f to 0. Using again equation 3, we substitute the given information. So we will have 0 equals 40 plus 5t minus 1/2 of 9.8t squared. Simplifying this will arrive to a standard form of quadratic equation 4.9t squared minus 5t minus 40 equals 0. The coefficients a, b and c are 4.9, -5, and -40, respectively. From here we can solve t using quadratic formula. Substituting the values and using the addition operation, will give a time of 3.41 seconds. For letter C, we're going to determine the final velocity of the sandbag as it hits the ground. We use equation 5, v sub f squared equals v sub I squared minus 2g y sub f minus y sub I. Substituting the values and getting the square root will give a value of negative 28.4 meters per second. We selected negative sign since the sandbag is moving downward as it hits the ground. Lastly, letter D, we will solve for the maximum height. So we set v sub f to 0. And using again equation 5, then transforming this appropriately to solve for the final position y sub f. So here's the transformed equation. Substituting the values, -5 squared divided by negative of 2 times 9.8 and adding 40. The maximum height reached by the sandbag is 41.28 meters. After reaching this position, the Now, it's time for your regular brain exercise. Good luck. Exercise number 6. Number 1, a ball is dropped freely from the top of a building. It is found that the ball hits the ground after 6 seconds. Letter A, how tall is the building? Letter B, what is the ball's velocity as it strikes the ground? Letter C, if the ball is thrown vertically downward at 10 meters per second from the top of this building, how long does it take to reach the ground and what is the ball's velocity at the ground? Number 2, answer part 100 of the previous problem except that the ball is thrown vertically upward at 10 meters per second. Number 3, Merlinda throws a ball vertically upward giving it a velocity of 5 meters per second. Letter A, how high does the ball go? Letter B, how long will it take for the ball to reach the maximum height of flight? Letter C, what is the ball's velocity as it returns to the thrower's hand? Letter D, what is the total time of flight?